Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 147 and 148. We are discussing free energy versus composition and activity versus composition diagram for the binary system AB. Okay? Bapu? Bappa? দাঁতে যেটা নিয়ে তো বাঁধলাম দাঁতের কৌটোটা হাউ ইট ইজ পসিবল আই ডোন্ট নো আমি এটা করতে গিয়ে নিচে রেখে যেমন ছিল রেখে দিয়েছে যেমন ছিল রেখে দিয়ে যা নিচে চলে যা কিছু করতে পারতো একটা কাজ যেমন ছিল সরি we are actually into lecture 147 and 148. We are discussing free energy versus composition and activity versus composition diagrams for the binary system AB, and we are considering isomorphous system. The diagram, phase diagram is given here, and today we are this is the diagram, isomorphous diagram, that is complete liquid solubility and complete solid solubility. And we actually discussed the free energy versus composition and activity versus composition diagrams for the temperature T1. We have already finished in the last class. Today we will consider the next temperature T2. T2, you see this? T2, you see, you have moved from this end to the other end, B, from A to B, you see, we actually come across here alpha phase, alpha is the solid solution, then this is liquid plus alpha, then the liquid solution. So we actually take up the similar procedure, that is, we will first try to draw the G alpha, G solid solution curve and G liquid curve, and we will compare their values and their positions, from which we will determine which phase is the stable phase. So this is the free energy versus composition diagram, and subsequently we will take up activity versus composition diagram. So this figure is 1A, then this will be 1B, and this is 1C, 1C, but this is for temperature, today temperature T2, and last day it was temperature T1, and so likewise it is 1C temperature T2, and last day it was 1C T1 for the temperature T1. So, so we will actually proceed in the same manner as last time. So okay, before this, let us see this diagram. Let me tell you a few things so that it may help you. Yes, this diagram. First of all, take a new look at this. This is the phase diagram remains the same. This temperature T2, no problem. Okay, and you have seen the stability, as I have already told you, stability domain is the solid solution domain, and this is the liquid solution domain, that is, you may call here 0 to A, the solid solution domain, then B to 1, liquid solution domain, stability domain I mean, and then this intervening region A to B is actually where liquid plus alpha coexist, means this is, both of them are stable. And they coexist at these two phase together at equilibrium. So liquid plus alpha. So this is alpha, liquid plus alpha, liquid. Repeat. Alpha, liquid plus alpha, liquid. So how I am actually, aim is same. Aim is the same. What is the aim? What is our aim? The aim is to draw or find G alpha, means G solid or G solid solution. variously you may call it. G alpha the G solid solution curve or G solid curve and the G liquid curve. So G alpha curve and G liquid curve. We construct these diagrams. What is the G? G is the integral molar free energy for this. This is our aim. So for this we need some preparation. Preparation is what? So this is the integral molar free energy axis plotted against XB is the mole fraction composition, and this is obviously XB is 0, this is XB is 1, this is pure A, this is pure B, no problem. And this is actually then what you have assigned. See here, this is very interesting case now. Previously, it is in contrast to the last days. Okay, so this temperature T2 is below the melting point of A. That means at this temperature, solid A is a stable phase, and solid A is the stable phase, and for B, liquid B is the stable phase because it is above the melting point of B. This temperature is below the melting point of A and then above melting point of B. So pure liquid A is the stable, pure solid A is the stable, and pure liquid B is the stable. So when we assign, so consider this A. So A, for A, pure solid A is stable phase relative to liquid A. So solid A or A solid has lower free energy than liquid A. So the one which has lower free energy will assign a value of 0. This is the consideration, and that we have already outlined. Okay, that is, so see, the lower one will assign a value of G. Lower free energy will assign a value of G, value of 0. So A solid, this 0 is A solid, because A solid is 0. Okay. Likewise, this side is what will be 0. So liquid B has a lower free energy. So we assign a value of 0 for the liquid B. This is the assigned value, not exact. Okay, absolute value we don't know, so we have to assign one. This A solid, then A liquid can be determined exact mathematically, and thermodynamically can be obtained. So this I have already discussed last class. So what I say, repeat, since this temperature T2 is below the melting point of A, so liquid A, solid A is the stable phase. So let us assign a 0 value of free energy for solid A. That we have done here. And here, as I have said already, since this temperature T2 is above the melting point of B, so liquid B has lower free energy than solid B. So assign 0 value for liquid B, the lower one assign. Then we have placed this is if A solid, if it is this, the A liquid will have higher free energy, and suppose this is the position, this is the A liquid, okay, free energy, and I have marked here GA0 liquid, and I have marked here GA0 solid. So GA0 liquid, GA0 solid. This can be determined, this distance, this difference can be determined. Last day I have said that from the value of enthalpy of melting and melting point of A. This difference can be exactly determined, but today we are qualitatively showing this value, or just we are showing some certain value. Okay, here should be above this, otherwise all will be mixed up and will be ruined totally. This diagram. So this should be above, and see the opposite here. See, this is this point. This is the B liquid is the 0, and B solid has higher free energy than B liquid. Okay, so where I have placed this? This is I have placed here. B solid I have written. B solid, and what is the free energy? GB0 solid. That is for pure B solid. This. So we have got 4 things. Ga0 solid, free energy of solid A, pure solid A, free energy Ga0 liquid, free energy of pure liquid A, Gb0 liquid, free energy of liquid B, pure liquid B, and here Gb0 solid, it is the free energy of pure solid B. So 4 points are marked here. So now what we can do, if we add connect this A solid and B solid, then this straight line is obtained. This is actually the expression. This actually represents XA Ga0 solid plus XB Gb0 solid. That is unmixed solid. Free energy of unmixed solid. Okay, XA and XB is, as you go each point you have XA, XB values. So XA Ga0 solid plus XB Gb0 solid. Likewise, if you connect this and this by straight line, this will be what? It is written here. You read this. I don't know. XA Ga0 liquid plus XB Gb0 liquid. This line. See careful. This straight line. Connect Ga0 liquid and Gb0 liquid. Connect. Then it becomes XA Ga0 liquid plus XB Gb0 liquid, which is the free energy of unmixed liquid. Now, next is what you recall this. You must have delta Gn curve, which is, since remember these are ideal solutions, already have discussed here, ideal solutions here. Okay, so what is this delta Gm ideal is T XA ln XA plus XB ln XB. So this is written here. You see this is for this one. So how to get now this G, say for example G alpha, how to get you this unmixed solid curve, this straight line will be added with this delta Gm. If you do this, so I repeat, you add this line, unmixed line with the delta Gm. I'll write it out, okay, so that you can note this. So you add this curve, unmixed curve plus delta Gm, that gives the G solution. Here it is solid solution alpha. So this plus this, which curve you generate? See, start from here to here. So this is the curve. See, repeat. This is the curve. This is your, see, I have written here G alpha. See, G alpha curve. Free energy, integral molar free energy of the alpha. Repeat. This one. Go with this one. And likewise, if you graphically add this curve, again the unmixed liquid is what? This line. And again delta Gm remains the same, being ideal, the same equation. So add this curve, this delta Gm curve with this unmixed curve for liquid, then you get what? Which curve? This together, this will form this and end there. So this is written somewhere, it is here. This is G liquid curve. Written here GL, G liquid. So GL you got, G alpha you got. So everything you have got. Everything at your command. So G liquid and G alpha, these two curves. So these two curves will be actually of our interest, and we will compare this to find the relative stability. And another thing you see, you see here, this point. See, I have actually projected this, and this one, this is the A, this is the B. So this point, if you see here, drop this point here, project here all the way. Similarly, B all the way down here. So AB, see this AB, see I have shown there, AB, point AB. A is this composition, B, A, B, this composition. This is actually called solidus composition, this is liquidus composition. Okay. So you see A to B, A to B. Okay, you have this A B. Now what you will do? So your next. So this will be written. Okay, I see up to this point. Then I will take up this A B. Okay, these two these composition segments, 0A and AB and B1. I call this way 0A, AB, B1. This I will. So we are up to this point. Clear? One is this is the G alpha curve, G solid curve, and this is the G liquid curve. These two curves will be considered. Okay, as a so let us actually go along with the instructions given in the last class. Let us follow the instruction given in the last class. Okay, once we get after instruction that we gave, that is with respect to the G alpha and G liquid curve, G solid and G liquid curve, how to compare these two to get the relative stability of the phases. Okay, so this part we will take up subsequently. So for the so it is. So I start this temperature T2 today. T is T2, temperature T2 today. Okay. The following points are to be noted. With respect to figure 1B, T2, now this figure. What is this? Free energy versus composition diagram. Figure B1, B T2 and figure 1C T2. This is activity figure 1C T2, activity versus composition diagram. Okay. Okay. So this. One, okay. As before, the curve G alpha is drawn by graphically adding the delta GM ideal curve with the unmixed with the delta G unmixed solid curve. That's a curve. What is this? That means G of solution is what? G of solution is actually the alpha phase solid solution is that is G alpha. That is G alpha. G alpha is what? delta Gm plus XA unmixed solid, GA0 solid plus XB GB0 solid. So repeat this XA0 plus XB0. So you clearly see, as I have already told you, XA GA0 solid plus XB GB0 solid is which one? This one, this straight line. It is written here, XA GA0 solid plus XB GB0 solid plus delta Gm is this curve, which is given by RT XA ln XA plus XB ln XB. This is delta Gm ideal. This is delta Gm ideal, I should write. It is actually delta Gm, but this delta Gm, since it's an ideal solution, so delta Gm ideal, but in general, you should write delta Gm, but you know what value it is given there, okay? So, these two curves, delta Gm ideal, this one, so what I want to say, see, recall this, delta Gm is what? Remember, delta Gm is what? G of the solution minus G unmixed. Unmixed is the, recall, state 2, this is the state, final state, and this is the initial state, state 2 minus state 1. So, solution, G of solution minus G unmixed gives the P&G chain due to mixing delta Gm. This is actually delta G system. This is G1, G2. Recall this. Recall delta Gm is the delta G. G2. This is G1, G2. So delta G is what? G2 minus G1. This, remember, this delta G is a delta G system. That is actually the mixing. And delta G of mixing. P&G of integral. P&G of mixing. Integral molar P&G of mixing. Delta Gm. Okay. Now this is actually, in case of ideal solution, this value is RT XA ln XA plus XP ln XP, and this is the curve. So this is okay. So this is so this, I think you have, you remember this, written this. Similarly, what you asked before, this is the one you got. So one curve is obtained. P&G of the curve alpha is obtained. Second is what? Oh, similarly, the curve GL, next is GL, liquid, L for liquid solution. That is the, the GM, I have written, you write this here, G alpha, this one, now what is the name of the integral molar, you write this. I'm sorry, I forgot. You know this is integral molar energy. Integral molar free energy. Free energy of the liquid solution L. Of the liquid solution. You can make your dreams come alive this winter. Solution L. L is a liquid solution, okay? So this is the G alpha. And here also write similarly, that is the, what is G liquid? The G liquid is the integral molar. Similarly write the integral molar free energy of the solid solution alpha G. Oh, similarly, so this is, I am very sorry, this is not liquid solution, this is solid solution. G alpha is the solid solution of the solid solution. Sorry, I am very sorry. Solid solution alpha. Okay, G alpha, since it is alpha, G alpha, this curve. Alpha is the solid solution, so it should be solid solution. And GL is the liquid solution. This will be liquid solution. Liquid solution L, of the liquid solution L is drawn. Similarly, that's right, in the same manner is drawn by graphically adding the delta GM ideal actually I tell you it should be delta GM delta GM, but since it is an ideal solution, so it is helpful, convenient, so it should be delta GM ideal. The rule is it is delta GM. If it is non-ideal, then delta GM. Generally speaking, delta GM non-ideal. Then it will not be RT XL and XA plus XB ln XB. It will be rather, it will be what? RT XA ln AA. Activity. AA and AB. This XA ln AA plus XB ln AB. And for ideal solution, A is XA, AB is XB. That's why we got this. Now recall this. So delta GM ideal curve is drawn by graphically adding the delta ideal curve with the delta G unmixed, this time unmixed liquid curve. That is again the right G solution. That is solution, G solution. That is G liquid is delta GM plus this one will be XA GA0 unmixed liquid. So XA GA0 liquid plus XB GB0 liquid. So no problem, absolutely no problem. So you have 1, 2, this 1, 2, 3 curves are available. This straight line, this straight line, this straight line, and this straight line 2 and delta GM. Then you get GL and G alpha, which is shown where this curve is the for GL, and this curve, as I show this curve, GL. See, maybe once more. Here it is. See GL, I'm going along this. This is a GL. What is the G alpha? This curve. How? This. And see they intersect. So about intersection I said something. So careful that I will use this. So before intersection and while and before intersection, you have some rule. When the curves don't intersect, there is some rule, and when they intersect, there is a different rule for equilibrium phase determination. This I discussed last class, okay, elaborately. So no problem. Second point is what would be, okay, 1, okay. In the composition range, zero A. Repeat. 0A. Here. This is the composition range. See here also. 0A. Who is the stable phase in this range? Alpha. So 0A. Let us see how it is obtained from free energy composition. How it is inferred or ascertained from free energy composition diagram. So in the composition range 0A, the curve G alpha lies below follow the curve GL, the curve GL, making the alpha phase relatively stable in comparison to the liquid L phase. Hence, in this composition range, alpha is the equilibrium phase. Alpha is the equilibrium phase. And you see clearly in the phase diagram also, alpha is the equilibrium phase. And you see what I said here, okay, G alpha, see, consider this composition, 0 to 8, which is below, which is above. This is this curve. This curve is for what? I'm very sorry. Compare this curve and this curve. Sorry. This is for G alpha. This curve is below this curve. Consider this segment, this composition segment. So this is above, this is below. This has a higher free energy, this has a lower free energy. This is a greater free energy, this is a smaller free energy. And this is at a higher position, this is at a higher position, alpha. I am very sorry, what is this curve? This is the liquid at a higher position and alpha lower position. Or liquid has a greater free energy and alpha has a smaller free energy. So alpha is the equilibrium phase. And also phase diagram also says this is equilibrium phase. Very good. So this is done in the composition range. In this composition range. Similarly, you consider the other extreme. This one you consider 0 to 8. Next you consider B to 1. The other extreme, because there is the same principle works applies. So just see what happens. So in the composition range, similarly, in the composition range, which one I am considering? Remember, I have just skipped now A to B. I'll come back to A to B composition range, but B to 1 let me finish. B to 1. So in the composition range B to 1, the curve, just like this you write, G liquid lies below the curve G alpha, making the liquid phase relatively stable. In comparison to the liquid phase. Actually, you don't have to write all the things because it's already there. G alpha below the, hence just directly conclude hence in this composition range, in this composition range, alpha is the liquid is the L is the equilibrium phase. L is the equilibrium phase. L is the equilibrium phase. These observations, these two observations, this and this, these observations are in accord. These observations are in accord with the what? With the phase diagram. Phase diagram is what? One figure 1A. Figure 1A. So this is why in accord. See, in this composition range, alpha is the stable phase, and in this composition range, liquid is the stable phase. So this is thermodynamically, free energetically obtained. Okay, so we are satisfied that this is the free energy composition diagram. Importance we understand, and this infers or this dictates which phase will be stable, which composition range. Now we have actually skipped the composition range A to B. We have skipped it, so that will take up now. Third, let us start here from here. Unnecessary. Third, remember now we will pick up. However, in the intervening composition, in the composition range, in the intervening composition range, AB, what happens? The two curves liquid and alpha, G liquid and G alpha, better, liquid and alpha, or G liquid and G alpha, in the form of G liquid and G alpha. So these two curves, what happens? Intersect each other. Now how do you see? See clearly, you see. See, follow this composition range. This AB, and go there. See, in this composition, what happens? What drama occurs? Yeah, what drama occurs? See. There is the intersection. At the moment this happens, you should note that integral molar free energy will not be the criterion anymore. The lower integral molar, the phase with the lower integral molar free energy will be the stable phase. No, this will not work anymore because they have intersected. And when they intersect, actually, you see the liquid and alpha, the alpha of this composition and liquid of this composition. Alpha of composition A and liquid of composition B. See here, alpha of composition A and liquid of composition B. This is called liquidus and this is called solidus. The curve for alpha. Okay. So this the composition is obtained from the liquidus. The liquid composition is obtained. So liquid of this composition, and from the solidus we get the composition of the solid alpha. These two composition, they coexist. Liquid and the phase diagram shows liquid plus alpha coexist. So criterion will not be which is above and which is below. Since they intersect, then you have to consider different criterion. What is that? I said not integral molar free energy. There are partial molar free energy will take effect. And partial molar free, and they coexist. It is not one will supersede other. One will upstage other. Liquid will upstage the solid, not like that. They coexist. Nothing will overshadow the nothing else. Okay, that liquid will okay. Liquid will actually this will be present. Will be preferably present compared to alpha, or alpha will be present preferably to liquid. This thing will not happen. So what will happen? That no, they will coexist. They will simultaneously be present. They will coexist. They will be present together. Togetherness. So this is the together. This. So and what is the criterion here? Partial molar free energy that you will get. This I will write you here. That will be the same for this. The liquid partial molar free energy of any component, say A, Ga bar liquid is Ga bar alpha. Gb bar liquid is Gb bar alpha. So in this case, so remember this is when they intersect each other is see, it is not that one phase will be preferably present compared to the other. This type of thing will not work. So however, in the intervening composition range, the two curves intersect each other. Then what will happen? Intersect each other, and the criterion, as I told you before, and the criterion for relative stability of liquid and alpha, of L and alpha, will not depend on the relative values of will not the relative values of relative values of G liquid and G alpha anymore. Instead, what will happen? Instead, remember, no one has precedence over the others. This is neither liquid has precedence over alpha or alpha over liquid. Since this does not happen, since they coexist, so integral mole of energy being higher or smaller will not be the criterion anymore. Instead, partial mole of energy will be the criterion. Instead, the equilibrium state will be governed by, our aim is to find the equilibrium state. Phase diagram is an equilibrium diagram. The total, this is equilibrium every point. This is equilibrium state, equilibrium state, equilibrium state. And equilibrium is obtained. Okay, see. So instead the instead what is this? Instead the equilibrium state will be obtained governed by the equality of partial molar free energy of each component. What is that? Oh, sorry, this is a part of the diagram. I'm very sorry, Ga bar alpha, I'm very sorry, is Ga bar. In fact, I'm going to write this. And this side is likewise Gb bar liquid is Gb bar alpha. So here, this I'll explain by drawing tangent. Okay, this part. How to get the partial values? So you know this one. So what is this? What is the criterion then? Ga bar in the liquid phase is Ga bar in the alpha phase. And similarly, not only A, B also have the same behavior. And how to get this one? Okay, Ga bar Gb. Now this will be satisfied how? Now before I write anything, you tell me how to get this. Yes, how to get the partial? You have the integral value. How to get partial? And they should be same. How to get partial? First of all, by taking a tangent. So suppose consider the liquid curve. This is the liquid curve. It is better I use this one. This is the liquid curve. So what you are doing? So you are actually taking a tangent here. Tangent. And this acts as a common tangent with the alpha. This is alpha curve. Solid. So this is a common tangent. And not only so, and the intercepts on this axis is known as xa is 0. Or I'm very sorry, xb is 0 axis or xa is 1 axis, means A, this one. It intersects this one. The intercept that we get is this value is given here, Ga bar. Since common, so they both have the same intercept, common tangent, so same Ga bar alpha and Ga bar liquid. The same value is actually obtained from the two curves, from the two different curves, because they have the same tangent, common tangent, and the intercept on this axis is called xa is 1 axis or xb is 0 axis, whatever you may call it, is Ga bar liquid or Ga bar alpha, and they are required. So this equality is obtained. The other side is also here. The tangent, go to the tangent, intersect here. This is xb is 1 axis. This is y axis, both are y axis, but this is the parallel y axis called xb is 1 axis and intersect here. So this is the Gb bar. Gb bar from what? Gb bar alpha or liquid? No, for common, since it is common. So Gb bar alpha and Gb bar liquid and Gb bar alpha, they are same. That is. So since the drawing a common tangent is feasible here, that means these two phase coexist. It is not one will disappear in favor of the other. No, liquid will disappear in favor of alpha, or alpha will disappear in favor of the liquid. As we saw here, the alpha liquid disappear in favor of alpha.
50 minutes.
And here liquid alpha disappears in favor of liquid.
Okay.
So this happens. So remember, but here they will be together. And what is this actually? So no, these are not. So they will coexist and they will be together. Okay, at equilibrium. Okay, so here. So let us note. You will note here. Note these two criteria. These two criteria will be simultaneously satisfied by drawing a common tangent to the two curves G liquid and G alpha at the two compositions XB is A and XB is B respectively. And finding the intercept on these two axes. What is the two axes? Finding the intercept on the XB 0 axis. On the XB 0 axis and XB is 1 axis. Okay, means this axis and this axis. Finding the intercept. Okay, then you will get this. Okay, these partial values and their equality. Both are obtained and their values, actual values actually. And 1 axis. XB is 1 axis. Okay, so this is this. Now next is fourth point about, so this is all about figure 1b. Now we take up figure 1c. Activity versus composition diagram. This is free energy versus composition diagram is all discussed. Fourth point will be about figure 1c, temperature T2. So in figure axis, fourth is okay. In figure 1c T2 for temperature T2, because both the solutions liquid and alpha both the solution liquid and alpha are ideal. The solid solution alpha which is stable in the composition range what composition range 0 to A in composition range 0 to A will exhibit ideal behavior What is that? What is the ideal behavior? What is the ideal behavior? What is the ideal behavior? You know? AB S is XBS. Right, naturally. ABS is XBS. That is the Gaussian equation. So let us explain this. First of all, see the projection. See the projection here. So see this person 0 A B B1. See here from here 0 A B B1. This is this is actually projected onto this curve here. Here the composition 0 to A to B B to 1. Okay, this is 0.5 actually. This is no problem. And similarly here it comes down further here 0 to A to B B to 1. So that means this composition is this composition. Which is stable here in this composition? Let us first of all discuss this. Which is stable here? Solid solution. So solid solution is stable. And this is which type of solution? Ideal solution. So what is the activity of B will be what? Activity of B in the solid solution, activity of B with respect to solid B as the standard state, activity of B with respect to solid B as the standard state will be what? Is XB. So you see, follow this diagram, follow first of all, then I will show you. This is XB in the x-axis as usual. XB is 0 to XB is 1. This is pure A, pure B, and this is your 0 to A to B, B to 1, coming from the top, coming down from the top. So this is no problem. And this is what I am presenting here on the y-axis, activity of BL. ABL, activity of BL means, what is the full meaning? Activity of B with respect to pure liquid B as standard state. This here is the pure liquid B, liquid B. Pure liquid B as the standard state. This full meaning, this I discussed last class also. So no problem. The same thing. There also I do this activity composition flow. So and these terms are well used. Activity of B liquid and activity B solid. They are used and they have the same nomenclature and same expression. Okay, and so this is this symbols actually described by this statement. And this is activity of B S. Then what it will be? Activity of B. Again, B. We are considering activity of B. You can draw activity of A also. There's this type of line will be obtained. Okay. If you can draw one, you can draw the other. Okay. Always present. Okay. So activity of, for example, see activity of A will be actually this type of line will be considered like this. Okay, first you follow this. Activity of B solid on the parallel y-axis. What is this? Activity of B with respect to pure solid B as standard state. This is the full meaning. This is again moving from this along this parallel y-axis, and this is 0 to 1. This has been given mark. Now you see follow. I tell you what, you since there are ideal solutions, liquid solution is see come across ideal solution, you come across ideal solution, and when ideal solution activity is mole fraction when the state under study has the same physical state as the standard state. So for example, you consider this is so you first draw activity of B's XP line. How will you draw? Okay, very easy. You just 0 to 1, 0 to 1. Just connect this. So this is the Raoult's law line, so-called Raoult's law line. So what I have written here, activity of B is XB line. Activity of, along this line, AB is XB. Since here this will follow activity of B liquid is in this segment liquid is stable, and if you consider liquid B as the standard state, so in this segment B21 where B21 in this segment AB liquid will be XB. Because solution is liquid and standard state chosen is liquid B, not solid B. Solid B you consider later. Solid B standard state later. So activity will be liquid. That means we are referring to this y-axis, this value, and which curve it is? The arrow means this curve. What is the name of this curve? I'll write it out clearly. What is the AB liquid is which curve? This. What is the name? Okay. If I may say O A B L here. So you see clearly here in the B21 here B21 it is liquid solution, ideal liquid solution. So and its liquid is a stable phase, and you consider AB liquid. So AB liquid will be how here what it will be? It will fall on the this AB's XB line. So this is the curve. See this curve. This part has not fallen. 0 has not fallen because this is solid solution, and here consider liquid as the standard state. Liquid B as the standard state. So it is the class. But here this segment there is no class. So this segment it has fallen on the AB is XB line. So this segment. And then it comes to two-phase region. Two-phase region, since GI bar is constant, no change. GI bar, so say common tangent actually means in this composition then you have GI bar, these values, given by this value, yeah, values. So GI bar, okay, so it will show horizontal line. So very easy then. Come down along the AB's XP line, then horizontal because two-phase region, okay. Then what happens? You have reached here, then connect here to 0, then you will get this complete line. Okay. So here what is activity B of with respect to liquid as a standard state will be 0 where at this end. But at this end you see it doesn't fall along the AB's XB line, it follows 0A. See? Different line. On the if we now consider the solid AB as the standard state, AB means solid B as the standard state, then solid B will follow Raoult's law when it will come across solid solution. Means this segment 0 to A you will see. So now solid curve is AB solid. Shown by which curve? 0 A B S. S here it terminates here, not L. See S. S for solid and L for liquid as it. So repeat. This is the curve. This is the curve S 0 A B S curve. What? I have given an arrow. This curve. I have shown this curve. This total is 0 A B S, and referring to A B S means what is the meaning? I have already said activity of B with respect to pure solid B as a standard state. Then this will follow Raoult's law. Activity is mole fraction. Which segment? In the segment of solid where solid is physically considered, the state under study is solid solution. So in this 0 to A, and you see clearly 0 to A, yes, this curve has fallen on the AB's XP line. AB is XB line, this. Then what will happen? Again, this two-phase region, horizontal line. Then what will happen? It will go to this point. This point is obtained from the, how it is obtained. Actually, last day I showed you this value of activity B solid will not be 1, because activity of B liquid is 1. Activity of B solid cannot be 1, because solid and liquid have different free energy standard. These are two different standard states. One has a greater value and lower value, so activities will be different. And this was given in the last class, their relationship. This relationship obtained. So we showed also this value. What is the value? Let us discuss this. What is the AB solid? AB solid is 0 here. 0 then goes this way, this way. This is what value? This XB. This is Raoult's law. AB is XB. XB is what? How much? XB is A. So XB is A. So this activity of B solid is A also. Then A remains unchanged. Horizontal line. Remember this figure, this curve is actually ABS, referring to the arrow ABS. So this is 0, starts from 0. XB is 0, solid. XB, this curve is here, start here. XB is 0. AB, rather, I am very sorry. AB solid is 0. 0, then go to XB is A, goes to XB is AB, I am sorry, AB is A, because AB is XB. XB is A, so AB is also A. AB is XB, XB is A up to this point, so AB is A. So how it is shown? Along AB is XB line, so straight. Then this is A. Then it is a horizontal line. That activity of B solid remains unchanged. Then what happens? It actually increases, but it will never reach 1, because
1 hour 7 minutes gone.
Achha, okay, take some time. Come back 10 minutes, 15 minutes later. 15 minutes later. And then it will be, then it picks up, okay, increases activity, but it will never be 1, because activity of B at this point, activity of B with respect to liquid standard state is 1, because this XB is 1. Here, 1. Right, this shown here. How can the solid, with respect to solid B, it will not be 1, because at this is here, actually the solid has the higher free energy, because it is above the melting point of B. So liquid is stable for B. So solid B has higher free energy than liquid B. That's why liquid is this is above melting point. This happens. So solid B with respect to solid, higher free energy with respect to higher value, activity will decrease. This I showed other day, and so this is this value. And also I actually give an equation. The relation between activity of B liquid and activity of B solid. When activity of B liquid is 1, what is the activity of B solid? Exactly e to the power delta G0 m for melting of B by RT. E to the power delta G0 melting, m for this m subscript for melting of B, delta G0 melting, okay, B by RT exponential. This is this value. So I repeat, or I will write it out, but I will repeat this. Start. So for AB liquid, across the diagram, this scale you are using. AB liquid. What is the? You are considering activity of B, not even A. A will be other way. A will be this way. This is another diagram. Okay. Here AB is XB line. So this line will be A is XA line. A is XA line. Similarly, you will have in the solution range, it will fall on the route. A is XA line, okay, like this. So start liquid. Start here from this end to that end. You go for this AB liquid, and which curve this for this? The arrow is given. So this. Repeat. This O A B L. This is the activity representation. How it is, okay? So and you also keep as a reference. This is activity of B is XP line. Whether it will coincide with this or not depends upon its actually behavior, and okay, and also the reference state. Since pure liquid B is the standard reference state for AB liquid, so in this segment we see this is solid phase. So phase understudy is solid, so liquid will not, AB liquid will not be XP, so it will not be like this. This will be, okay, this will be valid for solid. So this will be what then? How do you get this? It is better you come down from this side. This is purely AB liquid and liquid study understudy is phase understudy is liquid, so AB is XP fully work, because we have considered this solution is ideal. If it were not, then it will never fall. You will never fall. Okay, since it has ideal solution, and when ideal, so but remember I said AB is XB Raoult's law. The ideal solution equation applies when the state under study and the reference standard state has the same physical state. So that happens here, liquid solution. AB liquid we are considering and also liquid. So this B21 of course will fall on the AB is XB line, or you may call it Raoult's law. AB is XB line, I call it. So it falls, and then it is in this junction, this two-phase region, activity doesn't change, because see what happens here, as you move along, composition doesn't change. You know Lever rule and all such things. So when you move into this, gross composition changes, but liquid composition is triad here at B, and solid composition alpha is triad here. Only relative amount changes. Composition same means activity same, and so no change in active horizontal line. Always two-phase mixture, horizontal line. Then once you reach here, then you connect with this zero. It will be zero from this zero in either standard state you consider zero. So zero, this is the entire picture with respect to ABL. ABS, activity of B across the diagram with respect to solid B as the standard state. Start from this side is very easy. 0 to A is very easy because it is solid solution and your state under study is solid. State under study is solid, and reference standard state is also solid. What is this? Activity of B with respect to pure solid B as standard state. So reference standard state is solid and the state under study is solid. So this segment, you have AB is XP. It will fall on the activity of B solid. This one, remember this curve. This curve is what? Fully, I tell you, 0, A, B, S. 0, A, B, S. So this part will fall on the AB's XP line. It has fallen this time. And then again horizontal line for two-phase mixture. Horizontal line activity don't change. Composition doesn't change. Then you just connect this with the terminal value, which is actually obtained from this. Activity of B liquid value and activity B solid are connected by activity of B solid connected by this delta G0 melting. Last day I told you, from this you get up to this value, and this value exactly what? E to the power, means exponential. Delta G0 melting of B divided by RT. That's it. So this I will write here. Okay, this part. So this you have understood. But let me actually make up some damage to the diagram quickly. Let me draw this. Okay, no more damage. Sorry, bad, very bad. You understand, straight line. So, and then what happens? What else? Oh, yeah. See, this is A. This is B. This is A. This is B. This is S. This point is. This is L. Okay, and this activity. This is the ABL scale. Okay. So 0 to 1, and it is actually moving from this side. If you say 0 to say this value, exponential delta G0 melting B by RT. Okay, it is 0 actually here. It is 0. So this curve, again repeat, this curve which is OABS is for this scale ABS, and OAB L for ABL. Let us write few lines. Okay, then you will have clear picture. Okay. So while I am here, so where it is, AB is XB. Sorry. Now here you take this. It is better I go to the top. Remove this. Only temperature T2 remains there. You don't need this. Temperature T2. We are discussing this. What is this? After this. See? Is it in? So what we will the solution alpha which is stable. Like this. Start from this point. The solid solution alpha, right? The liquid solution L star from this point. The liquid solution L, which is stable in the composition range, right? Tell me B1 in the composition range B1 will likewise exhibit ideal behavior what is that? AB liquid is XP liquid. Okay, no problem. In the intervening, so two ends are discussed. Which two ends? 0 to A, B to 1. These are discussed. In one case it is, AB is XB, AB solid is XB solid, here AB liquid is XB liquid. AB solid is XB solid, this one, and AB liquid is XB liquid, this one. Okay? Repeat this. AB solid is XB solid, this one. AB liquid is XB liquid, this one. This, okay? B to L, okay? So in the intervening, now the question is in the intervening composition range, what is that in composition range? What is that? A to B, the phase mixture, what you will have in the intervening, okay? Here liquid is stable, solid is stable, and here both stable, coexist. So in the range, the phase mixture is stable, liquid plus alpha. The phase mixture, remove this. The phase mixture, liquid plus alpha is at equilibrium. The horizontal line, so as a result you get the horizontal line because activities don't change in the two phase region. Composition doesn't change, so activity also doesn't change at equilibrium. So the horizontal line connecting the two segments connecting the two segments of the ABL curve What is the name of the curve? ABL curve. Tell me of the giving by call it O A B L. O A B L given by O A B L appears because of the why horizontal segment appears. See why horizontal segment, what it says, so between two segment is what? This is one segment, this is another segment, and two phase region is actually intervening zone, so horizontal line will connect them. Okay, so appears horizontal line connecting the two segments occurs appears because of the equality. Equality, what equality? AB with ABL with respect to liquid standard state in the liquid phase is same reference state L in the which phase? In the coexisting phase, okay? Alpha. They are simultaneously present. Okay, so this is not only this, the explanation why you get this activity, same explanation is what? You get an explanation, quick, short. Explanation is what? I wrote here, I have removed this GB bar, liquid is GB bar alpha. GB bar alpha, here, this side, this is GA bar, this is other side is GB bar liquid is GB bar alpha. Also I wrote here, I have removed this. I have actually shown just okay, wiped out this, but GB bar, it was written a moment ago, GB bar liquid is GB bar alpha. So what you will do this, how you get this? Just quickly, or GB bar liquid minus GB0 liquid, because this is the with respect to is GB bar alpha minus same subtracted GB0 liquid, or what you get from this, or RT, this one activity of B no, this is actually not GB0, this is sorry, this is this liquid, this GB0 liquid, this is RTLN activity of B in where with respect to say liquid, you have subtracted liquid B, maybe liquid which phase? In the liquid phase with respect to liquid B as the standard state, either this is the standard state pure liquid B. The right hand side will be what? Is also RTLN activity of B with respect to same standard state, because same thing you have subtracted. And which phase? Alpha phase. Okay. You better be given very earlier. Okay. Now RT cancel, LN cancel, or the one that I have written here, activity of B.
1 hour 24 minutes,
Okay.
25 minutes.
Another slot, how many minutes? 10 minutes maybe. Activity of B
10.
liquid is activity of B. This liquid is the liquid lowercase. This one. Liquid, which phase? Is alpha phase. Since they are existing in equilibrium, so their activities are with respect to same standard state, they have the same activity. Same standard state is a liquid, and this is the two phases are coexisting phase are liquid phase and alpha phase. Activity is same. So this is the explanation. This ability. Similarly, you can write. Similarly, this horizontal line you will write. This horizontal line. Similarly, the horizontal line connecting the two segments of the ABS curve. ABS means this one means this diagram OABS. ABS curve given by ABS. ABS appears because of equality. What equality? Similarly, what it is? ABS now with respect to solid B as transited in which phase? Alpha phase and liquid phase. Okay, in liquid phase, this is the phase, liquid phase, and this is the AB solid B as the pure solid B as the standard state in this. Is what? ABS. See, ABS. What changes? The phase, liquid to alpha. Here also, ABL, lowercase l means this one. Explained here. Activity of B with respect to pure liquid B as the standard state. Which phase? In which phase? Activity of B. Which phase? Liquid phase. And here, same thing. Which phase? Alpha phase. They must be same at equilibrium. Because partial mole of PIG is same. Okay? That's why. Oh, sorry. In figure, I am very sorry. Oof, because in figure 1CT2. Sorry, in figure. Okay, this is activity of B solid. Oh, this is already done. Oh, sorry. This is previously. I am writing here. Okay, here. So remove these two lines. Remove this. This explanation, similar explanation. Do you want explanation? Explanation here, like before. Explanation is what? Again you write GB bar. Liquid is GB bar alpha. Right? The same way, right? What you subtract this time? To get this ABS, GB0S, not GB0 liquid unlike last time. GB0 liquid last time. This time no. To have this S with respect to pure solid B as the standard state. So subtract that. GB bar liquid phase. This L is the liquid phase minus GB0 what? Right. Solid. GB0 solid. Okay. Solid is what? Or give you or here. Explanation. Or here. Or what? Oh, sorry. Is what? Right hand side. Complete right hand side. GB bar alpha minus GB0S. Or what is? Okay. GB0S. Okay. Or what it is? This is nothing but RT activity of B with respect to solid B as the standard state. In which phase? The liquid phase. Is continue right hand side. Similarly, RT ln activity of B in the which solid B as the standard state in which phase? Alpha phase. Which phase? Alpha phase. Next, you cancel RT, ln, you get what? Or you get it like this, or AB liquid is AB with respect to solid B as the standard state in the alpha phase. Here AB with respect to solid B as the standard state in the liquid phase. Which I have written here. This is written here. This is the explanation. This is over. Local. This is explanation. Note. This is over. Note. In addition, the relation between, yes, the relation between XBL, this one, XBL and XB alpha, relation between XBL point B, that is point B actually, and XB alpha, what is that? Point, how many? Point B means points, lowercase b, sorry, point A, point B, these two compositions related, how they are related, how they are separated. This is greater clearly, B, concentration B is greater than concentration A, XB is B is greater than XB is A, clearly, XB increasing. How they are related? How many times it is greater than this? Such questions. How will you get this? They are related how? And that also depends upon temperature. T. They are related. So this question is taken up. Note in addition the relation between XBL point B and XB alpha point A. Point A is given by XBL is delta G melting by RT times XB alpha. This is the relation, liquid alpha. Okay. This is the relation. This is obtained from where? Last day class it was activity and activity. Activity of B liquid and activity of B alpha were separated by the same factor. From which you get this, okay? Or following the relation, this is very important. This is very important relation. Your question is this composition and this composition. This composition, liquid, solidus, this is liquidus. Composition A, composition B, how they are related? Answer is this. XBL is what? B, point B. And XB alpha is what? Point A. This is related. Depends upon the temperature. If it is T2, this, then change the temperature, it will change, okay? Depends upon this. Okay, this is very good.
1 hour 34 minutes gone. 35 minutes.
5, 6 minutes, 10 minutes, 7 minutes.
10 minutes.
No, 10, maybe less than. Okay. Following the relation, this can be obtained following the relation. Last class, following the relation. Following the relation between ABL ABL between ABL ABL and ABS. This is AB with respect to liquid B as a standard state and a bit of B with respect to solid B as standard state. What is the relation? Remember this? This was discussed last class. From this you have similar relation. From the relation ABL and ABS obtained previously. Last class. Similar relation. Here. This is this equals to this times this. This equals to this factor times this. Also you see, okay, XBL is the composition. ABS is XBS, XB alpha, S means alpha, and ABL, XBL, that's the composition of the liquid phase, okay, XB liquid phase. This you can check back, okay, and this how to get this, always anytime activity, how they are related, depends upon the standard state changes. So recall this actually just go back, this GB bar is GB bar, I wrote this, and GB bar minus GB0 liquid is GB bar minus GB0, okay, solid, and okay, this I wrote actually GB bar by that. Recall GB bar is GB bar identity, then GB bar minus GB0 solid standard state, solid B standard state, minus is equals to GB bar, oh no, GB bar is what? GB bar is what? Sorry, let me write. GB bar is GB0 solid B standard state, Just I am revising this. GB0 plus RTL activity of B with respect to solid B as standard state. Solid B as standard state is the left hand side. Left hand side expanded. GI bar is GI0 plus RTL activity equals to what? Right, similarly GB0 B liquid B as standard state plus RTLN AB, but with respect to this standard state, with respect to right liquid B as standard state. From this you will get this. This actually these two terms makes for delta G0 G0 solid B as this was solid B. No, this is actually GI bar. Actually, you don't have to write standard state solid B, pure solid B. This is pure liquid B. Let me write pure solid B, GB0, pure solid B. And this is plus RTL activity. This is with respect to pure solid B as the standard. If you write pure, you can add. And here GB0 pure liquid B plus add RT Ln activity with respect to pure liquid B. Then activity with respect to pure liquid B as standard state. As standard state. If you take this to the right hand side, so GB0 liquid B minus GB0 solid B is what is delta G0 B melting. Okay, this is, remember, that's why I give a hints actually. This hints means last day's class you get this. Recall. This is recall part. Okay, recall. Okay, good, very good. Problem previous. This part is over. Now temperature T2 discuss, temperature T3. Temperature T3. T3 is what? This one, which is stable? Alpha. And across the composition. Like T1, which is the stable? Liquid across the composition. No existence of alpha, solid. And here no existence of liquid, pure liquid, alpha base. So just, I will not actually repeat what I did for temperature T1, I am just giving an outline. Temperature T3, the construction of temperature T3, shall I, this is the end of this isomorphous system. Temperature T3, maybe what shall I write? Temperature, I start writing here. The construction of it is better right here, huh? Remove. Temperature T2 is over, so remove this. Temperature T3, right? Temperature T3, just I'll give the outline. The same way you did. You drew the diagrams, these two diagrams. For temperature T1, do the same way. Temperature T3, so the construction of constructions of free energy versus free energy versus composition and activity versus composition diagrams will be done similarly to those in the case of temperature T1. Just repeat like temperature T1. Only difference is what? Only the G alpha curve will lie below the curve, on the G alpha curve, below the G L curve. Making if the alpha is below and liquid above means alpha will be the stable phase, and as we see in the diagram. So making alpha the stable phase across the entire composition. Entire composition, that is xb is 0 to xb is 1 of the phase diagram. Okay, of the phase diagram. See, entire across this T3 temperature, across the composition, alpha is a stable phase. Very good. So this is only this difference. Previously it was for T1, liquid was a stable phase. So free energy of curve of liquid was below the free energy curve of alpha. G alpha was above G liquid curve. So liquid was a stable phase. Here the opposite will occur. G alpha curve will be below the G liquid curve. If you draw this, you can do it. Do yourself, right? So this diagram. So this is, with this we have completed this isomorphous system. Next class I give you what? So one, next class, second one. Next class, second item, eutectic system. Binary. It is still binary. I have already mentioned that it is a binary system again. We will discuss. Eutectic system. Bapu, done. Eutectic system with limited solubility. So with this, actually this is the next class. This will be taken up, this one. So this is over. So I have drawn a line here, means this topic is isomorphous system is over. So continue. Second item, second topic, I will second type of phase diagram will consider, and still another, the third type will be considered after this is over. That is, okay, where chemical compound formation is seen in the phase diagram in the intermediate composition range. That is down the road, but this is the next class. Okay, thank you very much. Thank you for your cooperation and your interest. Okay, see you next class. Bye. Okay. Oh, okay.